On the exam, how would I lose marks on this graph? Yeah, I don't have an X and Y axis and the arrows. You also have to show scale, but this already had scale. So X and Y axis as well. Yes. Okay, so I plotted 2, 4. Does anybody think they know how to plot the function negative f of x? This is f of x right here, just so you know. How would I plot negative f of x? Okay, I hear -2, -4. Does anybody else want to take a guess? -2, -4. -2, 4. Anybody else want to take a guess? What's f of x a fancy name for? Well, I even have a poster back there. So what's happening here? Y is going negative. That's what it's saying. It's saying, here's f of x. I'm going to stick a negative to the y's. So what's my new point? 2, -4. You got to think of a function. F of x is the output. When it's inside, it's the input. So I'm actually changing the output of it. So when 2 goes in, 4 comes out in the original function. If I'm graphing negative f of x, 2 goes in, and I'm changing the output now. So now it's 2, -4. So 2, -4 would be down here. And that is a reflection over what axis? X. It's changing the y, but it's a reflection over the x-axis. Okay, how about f of negative x? Oh, so we're getting smart here. So yes, I'm changing the input, so that's my x. So 2's not going in. I'm actually changing the 2, and it's becoming -2 is going in, and 4 is coming back out. So what is that a reflection of? Y. Okay, so from this time on, you need to know that f of negative x is a reflection over the y-axis, and negative f of x is a reflection over the x-axis. Okay, so a big mistake a lot of people make is they think the inverse function, that's an exponent. It's not. Where have you seen this -1 before in grade 11? Here we go. Huh? Yeah, the inverse sine, inverse cos, inverse tan. A lot of people call it second function, which is so bad. Don't ever call it second function. It's a second function of your calculator, but if you look at your calculator, it's actually the inverse function. Anyways, so inverse function, this is not an exponent. It's a notation. It does not mean 1 over f of x. Remember, if you have 2 to the power -1, and that's 1 over 2, that's not what this -1 means. It's a notation, just like on your calculator it says inverse cos, inverse tan, all that, right? Okay, so do you remember what inverse means? Maybe you don't. It's the method of undoing something. So this original function is if 2 goes into the function machine, 4 comes out. So if I want to undo it, what's going to go back in? Okay, watch this digital. 2 goes in, 4 comes out. We're going to go the other way. So what's coming back in? 4 goes in, 2 comes out. We're supposed to get where we started with 2. It is a full circle. So if I want the inverse, what would my new function be? Two, 4. We just said it. 2 goes in, 4 comes out. 4, 2. There you go. Okay, so 4, 2 is right here. We're still talking about the original function 2, 4. So what is that a reflection over? Which line? Huh? Yeah, the diagonal. Do you remember what that equation was? Y equals x. Okay, so just to recap here, does everybody see the same distance from 2, 4 to this line is the same from 4, 2 to that line? Same with if I go this way, 2, 4 to over the x-axis is the same distance from here to the x-axis, yeah? That's how the mirror image works. Yep. So what in fact am I doing when I'm doing the inverse? Look at 4, 2 to 2, 4. You're swapping x and y around. Yeah. Okay. So now we'll recap here. Y equals negative f of x. That is a reflection over the x-axis where what changes? What changes? The y value. And what happens? It changes sign. So if we talk about mapping notation, xy becomes x negative y. Old point, new point, right? So here's my made-up function here. It says w. It's a piecewise function of how many functions? Yeah, 4. 1, 2, 3, 4. We could come up with the equations if we wanted, but we don't need to. Huh? There you go. Okay, so again, if this is negative f of x, what's my new point? Xy becomes x negative y. So let's get some points on here so that we can reflect it. Let's pick 5 points here. So negative 3, 2 becomes what? Negative 3, 2 becomes negative 3, negative 2. Very good. Yes? Here's my mirror. Do you see that? There's my mirror. Okay, where's another point? Negative 1, 0 becomes, well, 0 switches sign. It's still 0. You see? What's that called? An invariant point. Yes? Then we have what? 0, 2. What is that going to become? 0, negative 2. So I should probably connect this as I go, just so I don't lose track of this. And once you get really good at this, honestly, to fill out the table of values, it's probably more work than just reflecting where it goes, right? So, but I'm going to continue just in case anybody's having trouble here. So this 1, 0 becomes 1, 0. That's another invariant point. And then my last point here, 3, 2 becomes 3, negative 2. So there we go. And then I have to make sure I have arrows to finalize that. Okay, so like I said, you can use the mapping notation, meaning this table of values looking kind of thing, or you could just, you know the mirror is here, so just start reflecting. This is much easier if you get it, right? Okay, next example, example 2, what is that? G of x equals x minus 2 times x plus 2. It's a quadratic. And what's special about this quadratic? Oh, yeah, you're saying if I multiply this out, this is the difference of squares, x squared minus 4. Yeah. Okay, so say you didn't multiply it out. What does this form tell you? The x-intercept. So you know it's going through 2 and negative 2, yes? Nope. Okay, so did you realize that between 2 x-intercepts is the vertex? Well, maybe you didn't know this. When you draw a parabola, parabolas are all symmetrical, right? And right through the middle, everything's the same distance. So if you have 2 x-intercepts, right here and right here, the vertex has to be halfway between the two. Does that make sense to you? Okay, so although it's pretty easy to multiply it out, and I know it's just a base parabola that got shifted down 4, but say I didn't know that, I could figure it out because halfway between negative 2 and 2 is 0. I could plug 0 in, and what do I get there? Negative 4. Okay, and this is a base parabola like this. How do I know that extra point here? Yes, because of the pattern of a base parabola. Remember I said to get you guys to memorize 0, 0, 1, 1, 2, 4 pattern? Yes? How do I know it's a base parabola? When I multiply this out, I don't have a coefficient. It's not stretched. So I know I just got shifted. So a base parabola that got shifted will still have the same shape as 0, 0, 1, 1, 2, 4. See, 2, 4. Okay. So now we're going to graph negative g of x. What does that mean? What does that mean? Where is it reflecting? So watch when you guys do assessments. Changing the sign of y's does not mean it's a reflection over the y-axis, right? You are changing the y's, but it's a reflection over the x-axis. This is where my mirror is, right? Yes, the x's are not changing. So these are invariant points. This is 3 down, so it's going to go 3 up. This is 3 down, it's 3 up. This is 4 down, so I have 4 up. So does everybody see that? Where's the rest of my graph? Is it going to be the same as this? No, this is going to be reflected down, right? Does everybody see? Okay, so what's the equation of my new reflection? Look at you. Yeah, negative x minus 2, x plus 2. Or what else could I have? So is it just negative x squared minus 4? It would be in brackets, yes. Okay, I can't even trick you. Negative bracket x squared minus 4. Or you could multiply it in and you could have negative x squared plus 4. Do you see it's a parabola that's upside down? Yeah? And what were the invariant points there? How about negative 2, 0? And 2, 0? Yeah? Okay. Now we're going to do reflections in the y-axis. It's changing the input, right? So reflection over the y-axis occurs when every what value changes sign? X value. Reflection over the y affects the x. Okay, so old point is xy, new point becomes negative xy. So you guys want to try this one? Where's the mirror this time? The y-axis. So you could do a mapping notation, but don't you think it would be easier just to reflect it by eye? So this distance here becomes over here. The invariant points, have you noticed, they're always on the axis? Have you noticed that yet? Yeah. So, looks like that. This goes over here. You keep on going. Yeah? So what's my invariant point this time? 0, 2. Make sure you use brackets around your coordinate, otherwise you'll lose a half mark. Okay, let's move on. Easy, right? Sure. Okay, how do I graph this? What is it? It's a parabola again with what kind of zeros? 2 and negative 4. And where is my vertex? Halfway between. So where is that? Negative 1. How would I figure out how low it goes? Plugging in what? Negative 1. So I need to find h of negative 1. So that's going to be negative 1 subtract 2 times negative 1 plus 4. So I get negative 3 times 3. Negative 9. Way down here. Whoops, I put it in the wrong spot. I put negative 1 in for x because it's halfway between the two zeros here. Can anybody tell me what the x-intercept is? Sorry, the y-intercept. put 0 in for x, what do you get? -8. So then that would be a mirror over there. Do you see that? So this is a base parabola. If I multiply this out, I get a base parabola. So it still has the pattern of 0, 0, 1, 1, 2, 4, 1, 2, 3, 4. So then at least you get a little bit more of the shape here. Yes? Okay, so where are we reflecting it if we're finding h of -x? Yes, the mirror is on the y. You don't have to draw the mirror, I'm just trying to show you. So, how do we do this? I'll use green again. So, if this is 1 over, we go 1 over the other way. Yes? I have an invariant point right where that is on the axis. This is 2 over, so I have to go 2 over here. What happens about the x-intercepts? Yeah, the -4 becomes +4, and the +2 becomes -2. Again, here we have 1, so we go 1. Here we have 3, so we can go 3. 1, 2, 3. So then here we go. Bada bing, bada boom. So this is h of -x, and this was h of x. Okay, we good there? We have to come up with the equation. So, who can tell me what the equation of h of -x would be? Okay, I'm sorry, say that again. Oh, like that? No. That would be -h of x. Okay, so I'm hearing it would be x plus 2, x minus 4. So this incidentally is correct, but it's a fluke answer. You're not supposed to change the signs of the numbers, and there's an example coming up where that's the case. What you're actually supposed to do here is you're supposed to, you see the input is changing, the -x is actually changing. So the correct answer is -x minus 2 times -x plus 4. But see, this is why it's the same. If I factor out a negative out of this one, I get negative bracket x plus 2. Does everybody see that? I factor that negative out. Yes? Now if I factor this negative out, this negative becomes a plus, and I get x minus 4, which ends up being what you said. Like I said, you end up fluking the answer. I need to probably change this question, but I think it's a good learning point that you got to make sure you're changing the x. That's what's changing. So there's an example coming up where there's nothing you can actually do. So what's my invariant point? That would be 0, -8. Okay. Symmetry. Okay, so this is a great calculus topic. One-to-one functions. So can anybody name all the functions they know up to this point in their mathematical career? I don't think anybody knows factorial, by the way. I was thinking, well, you're thinking literal functions. I was thinking about all the functions we graph. So can you name some of those? Quadratics, linear functions. What else? Okay, so trig functions. Somebody trying to get it? Trig functions. Radical functions, rational functions, reciprocal functions, absolute value functions. You guys know way more than that. Okay, you do so. Okay, so going back to grade 10 now, do you remember what a function is? There's always going to be somebody that knows. The vertical line test. See, she remembers some stuff about the functions. What you're trying to say is for every input there's only one output, maybe, or for every x there's only one y. The vertical thing. Okay. Yeah. Okay. So if I look at a blank sheet here, here is my x-axis and y-axis, and here's my function. Would that be a function? What do you mean not in the middle? Oh, because it looks too vertical? Okay, I'll make it a little bit more exaggerated then. Okay, this is supposed to be a function. If I take my pen and I do a vertical, it'll pass. For every x, there's only one y. Like when I put it into the machine and I say, if 2 goes in, I don't know, I can't really read it, but I know that 3 would come out. It's not like I wouldn't know what would come out. That's how I know it's a function, right? Okay? So what we're doing here is we're going to learn about a new thing. It's called the one-to-one function. That's when the inverse is a function. Let's go look at this. How would I graph this inverse? We just learned how to graph the inverse. Yeah. Switch the x and y. It's a mirror on the y equals x line. I'm doing this so roughly at this point. So if I look at it this way, I don't know. It's kind of like this, right? Somebody can correct me if I'm not the best drawer, but it kind of looks like there's the inverse, yeah? So is my black function here a function? Is this black thing a function? Look at it. If you go like this, it would fail. Some arbitrary function. Okay, is the black function a function? No, we can't even call it a function. It would fail if you do a vertical here. So what happens if I told you, you could have told me before I drew the black function there that it wouldn't have been a function? I'm sorry? Oh, look at this guy, hey? What would that be called then? What kind of test would that be? The horizontal line test, yeah. See, the red would have failed the horizontal line test, so this black, we knew before we drew it, was going to fail being a function. Okay, so let's go back here. So a one-to-one function is a function whose inverse is also a function. Let me read that again. A function y equals f of x whose inverse, f to the minus 1 of x, is also a function, is called a one-to-one function. So that means that the function and its inverse are both functions. That makes it a one-to-one function. So this function for every y corresponds to only one x. So the original function, for every x there's only one y. For the inverse function, you would be looking at for only every y there's only one x. So to determine whether a function is one-to-one, it must pass the horizontal line test. Well, we are in a second. Can you tell me if this is a function here? Yes. If it fails to be a function, then you don't have to go any further because it can't be a one-to-one function if the original isn't a function. Does that make sense to you? So this is a function. Is it one-to-one? Now do the horizontal line. Yes. Okay. How about this one? Is this a function? Yes. I don't know what I was trying to write there, but yes. Is it one-to-one? No, it would fail the horizontal line test, right? So even function, a function whose graph is symmetrical with respect to the y-axis. So if the original function is the same as a reflection in the y-axis, then it's considered an even function, and it has all these nice properties that you'll see in calculus next year. So what would be an even function? What would it look like? Does anybody know what this what this is. Oh, that's not exactly great. Let me try it again. It is you're close. It's actually a cosine graph. That's an arrow there.
All right.
And if you look at this, if I were to reflect this in the y-axis, do you see? It's the same graph. Like this would reflect to this, and this would reflect over. It's the same graph. Another one would be something like absolute value function. You see if I reflect it over the y-axis, it's exactly the same. Can anybody name another one? A parabola. And the parabola could be anywhere. I don't know why I have a big graph here, but you could have it here if you wanted. It doesn't have to be at 0, 0. But I think I was supposed to have the cosine there, yeah. Okay, so does everybody see if I reflect this parabola that has a vertex on the y-axis, it would be an even function? Okay, odd functions say if I reflected over the x-axis, it would be the same as a reflection over the y-axis. Or you could also state it this way. The original function, if I actually reflect it twice, it would be the same. So I'll give you an example of what it is. Actually, I'll do it over here. Something like this. This is a sine graph, yeah. And we'll go into this in this unit, in this course. But anyways, do you see if I reflect this, if anybody takes physics, you learned that this is a crest and a trough, right? Well, in math, it's a max and a min. Anyways, so you get wavelengths in grade 11 physics. So if I reflect this over the y-axis, it would come down here. And then if I reflect it over, sorry, I said that wrong. If I reflect this over the x-axis, it would come down here. And if I reflect it over the y-axis, it would be over here. Take any point, reflect it. It would be the same as the other graph there. Okay? Can anybody come up with another odd function? New. But something you're going to learn this year is a cubic function. You see, if I reflect that and reflect it again, it would be the same graph. Yes? And then you can just make, I don't know, I'm just going to make up another one. I call it, now all of these are symmetric with respect to the origin. This means that the reflection over the x-axis is the same as a reflection over the y-axis. Okay, so now we're going to do this algebraically. What's the new function if I reflect this over the y-axis? If it's a reflection over the y-axis, what am I doing? Negative f of x or f of negative x? F of negative x. Does everybody agree that's what I'm actually figuring out? So how would I figure this out? How would I come up with a new equation? Do you see here's the one where you can't switch the signs of the numbers? What are you actually doing here? You need to change these x's into negative x's. So you get negative x, the whole thing cubed, plus negative x. And then we're going to simplify that. And what do we get? Negative x cubed minus x. Which actually, if I factor this out, you'll see that I ended up getting negative f of x, which means this was an odd function. That's a side note. Okay, if I reflect it over the x-axis, what am I doing? Negative f of x or f of negative x? Negative f of x. So how do I figure out the new equation? And negative in front of the whole thing, but make sure you use a bracket. So negative bracket x squared plus 1, which becomes negative x squared minus 1. Here's a function. Did you realize a function could be just 3 points? Yes? Like that in grade 10. So if negative 3 goes in, 4 comes out. 2 goes in, 7 comes out. Here's a function, right? 8 comes in, 6 comes out. Okay, so this was an actual question from the provincial exam that everybody did brutal on. So I put it as an example because I think it's a good question. Anyways, given this function, state the domain of the resulting function after f of x is reflected through the y equals x line. Does anybody remember what kind of reflection that is? And it reflects over the y. Inverse function, right? This means it's the inverse function. And what do we know about the inverse function? It's over the diagonal. It's a reflection over this diagonal. Yes, if we have an old point xy, it becomes yx. They switch spots. So what do you think happens to the domain and range then? They switch. So can anybody tell me the domain of the resulting function after it's been reflected through that line? Anybody? 4, 7, and 6. Very good. Okay, do you get it now? Okay, so the domain would be of this function -3, 2, and 8. And the range would be 4, 7, and 6. Domain is the x, range is the y. So if I'm switching the x's and the y's around, you see the domain of this function becomes the range of this function, and the range of this function becomes the domain of this function. You don't have, well, you probably should, but you don't have to. Like, you wouldn't get marks taken off if you didn't put it in the order. Okay, do you remember absolute value functions? Absolute value 4 is 4, absolute value -6 is 6. What's the definition of an absolute value? And that's what a lot of people think, and it's true. What are you actually measuring? Yeah, the distance from 0, very good. Okay, so that's why it's always positive, because you're measuring a distance. The absolute value number is always positive or 0, of course. The absolute value of a function makes all what positive? No, not all y values positive. Because again, f of x is just a fancy name for y. So if I'm absolute valuing the function, I'm absolute valuing the output, right? So this is a half reflection. The y values that are blank stay where they are. That are positive stay where they are. And the negative y values are reflected over the x-axis. So how would you graph this? Well, let's first graph the line 2x minus 2. So how do you graph 2x minus 2? You put a point on -2, and you up 2 over 1, up 2 over 1, up 2 over 1, just to get a little bit of a... So there's my line. Everybody agree? This is my f of x. So how would I graph the absolute value function? Well, this would stay the same. All positive y values stay the same. And what happens to my negative y values? It gets reflected over the x-axis. And that's how we get that v out of that line. So that is... Do you remember how to graph this parabola? Okay, so you do know how to graph f of x equals x squared minus 4, though, I bet. How do you graph that? Yeah, it's a base parabola that got shifted down 4. Has that nice pattern of 0, 0, 1, 1, 2, 4. Here's my 2-second parabola graph. I don't know. Okay, so how would I graph now the absolute value of that? Whoops, I did that wrong. Does everybody see that would be, if I absolute value the f of x, that's the absolute value of x squared minus 4. So y values stay the same. And what happens to below there? It flips up. Very good. And it is not a loop-de-doop here. This is a jagged edge cut off right here. So make sure it comes to a point. You'll lose marks. Like if you make your graph like this, you'll lose marks. It should be like jagged. Sharp. Okay?